Hi, my name is Viktorija Paneva from the University of Bayreuth, and I will present the Levitation Simulator, prototyping ultrasonic levitation interfaces in virtual reality. This was a joint effort with Myroslav Bachynskyi and Jörg Müller. By merging physical and digital worlds, levitation interfaces open an entire new avenue of possibilities in the way we display and interact with information. However, due to their limited availability and complexity, we have not been able to tap their full potential. As a solution, we propose the Levitation Simulator, a tool that can be used by researchers, designers, and students to iteratively develop and prototype ideas for levitation interfaces in virtual reality, and even conduct user tests and formal experiments. Only after the development has converged, the resulting system can be validated using a real apparatus. The games that you just saw were an example of content that we developed in the simulator and then implemented on the real apparatus. And in this process, the Levitation Simulator was very useful to us by allowing us to efficiently test and set game parameters, such as size of target, velocity of particle, or control to display ratio. But first, what are levitation interfaces? Levitation interfaces use acoustic radiation force to trap levitating matter in midair. The levitating matter is composed of individual levitating particles, analogous to pixels on a 2D screen. The particles are suspended in midair using focused ultrasonic waves, emitted by opposing arrays of phase transducers. Some of the advantages of levitating displays include direct manipulation of physical visualizations, unadorned interaction, meaning that the user can interact with the display with their bare hands without the necessity of controllers, gloves, or other gadgets, transparency. The display allows good visibility from many angles, encouraging collaboration and social interaction. And lastly, it offers all natural depth cues, and contrast, focus, and illumination are all correct. Levitation interfaces can be employed in diverse contexts. The first example features floating charts, a modular display where levitating particles are used to encode data points on a dynamic chart in midair. Freeman et al. Proposed using a levitation interface to enhance the appearance of static physical objects. And thirdly, Levi props are tangible structures that can be used as interactive elements or dynamic projection surfaces. Some interaction techniques for levitating displays include LeviCursor, a levitating physical cursor which can be used for selecting objects in 3D space, and point and shake, an interaction technique for selecting objects in the display, where visual feedback is given in the form of side-to-side movement. This and other interaction techniques can serve as building blocks for developing new applications. In the couple of years of working with levitation interfaces, we have gotten a good sense of the challenges that newcomers wishing to develop for this type of interfaces would be faced with. Namely, building and maintaining interactive levitation interfaces requires financial resources, time, specific technical expertise, knowledge of acoustics, microsecond synchronization, and sub-millimeter calibration of all the system components. And in addition, the systems are difficult to debug. In case of problems, the only visible effect is that the levitating particle shoots out of the acoustic field in an uncontrollable manner. So, these challenges can pose a barrier for designers, artists, game developers, researchers, and students to start experimenting with this novel technology. For a solution to this problem, we turn to virtual prototyping, an approach that has been proven successful in other disciplines. For example, using a virtual simulation to work with a complex physical system is a common practice in the automotive industry, as the work by Dessau et al. From 1999 shows. In contrast, there are only a few studies involving virtual prototyping in HCI. One example is a study that compares AR and VR prototyping for a maintenance panel of a rock crushing machine in terms of ergonomics. So in this work, we developed a model of the movement dynamics of a levitating particle in an acoustic field. We used this model to create a simulator of the physical interface. One of the unique aspects of levitating interfaces is their 3D nature, and in order to preserve this property, we choose to build the simulator in virtual reality, in the Unity game engine. In the next step, we validate the results obtained in the Levitation Simulator by comparing them to the real prototype in 2 user studies. In the first study, we conduct a Fitzlow type pointing study to obtain a quantitative measure of the pointing performance that can be achieved with both systems. And second, we investigate the differences and similarities in the engagement with levitation applications in the simulator and in the physical world. The real prototype consists of 2 opposing rectangular arrays of ultrasonic transducers, a controller board, and 6 OptiTrack Prime 13 cameras. A C application receives input from the motion capture system and generates the corresponding acoustic trap positions. To be able to generate a physically accurate rendering of the levitating particle in the simulator, we need to derive a mathematical description for its dynamics. In the video, it can be observed that the behavior of the levitating particle in the acoustic field is comparable to a point mass attached on an elastic spring. The acoustic force acts as a restoring force that returns the particle back to its equilibrium position. Luckily, such systems have been studied in detail and can be described with the well-known equations, taking into account the spring, in this case the acoustic force, the air drag, and any external force acting on the system. Next, we see a plot of the acoustic force in the 3 spatial dimensions. Since we are interested only in the behavior of the levitating particle in the vicinity of the acoustic trap, for simplicity, we approximate the acoustic force using a linear function. The Levitation Simulator consists of 2 modules, an interaction module and a simulation module. Users can interact with the virtual interface via the motion capture system or VR controllers. The simulation module reads the new trap position via a UDP socket and uses the dynamics model to calculate the particle position, which is communicated back to the interaction module. Next, we evaluate the Levitation Simulator with users and investigate what are the differences in pointing performance between the Levitation Simulator and the real prototype. We conduct a Fitzlow type pointing study where participants performed repetitive aimed movements between 2 3D spherical targets of varying size, resulting in 3 different indices of difficulty. And we use a within-subjects experimental design with 2 movement directions, front-back and left-right, in the 2 interface conditions, real and in VR. The graph shows the Fitzlow models for the 2 conditions. And we see that both conditions are characterized by similar movement times and throughput, with a slightly higher throughput in the real condition. We also notice that movement time increases faster in VR with increasing index of difficulty. This is possibly due to the limited depth cues in the virtual environment. In the interviews, some participants reported having difficulty estimating the exact depth of the levitating cursor relative to the targets, especially when the targets were small. The research question of the second user study is what are the differences in user engagement between the Levitation Simulator and the real prototype? In the second study, we investigate how users engage and interact with the same content presented on a real and virtual levitation interface. For the purposes of this study, we designed two levitation games. The first game is called BeadBounce. In this game, the player directly interacts with the levitating particle using a racket. The player task is to hit the ball before it wanders off to the so-called danger zone, which is denoted by the black pole in the middle of the field. In the second game, LeviShooter, the player shoots at a moving levitating particle with a laser gun, and after each successful hit, the difficulty of the game increases by increasing the speed of the particle. We let participants play each game on each interface for a maximum of 5 minutes, and then we administered the user engagement scale. The results show that for the BeadBounce game, the only significant difference between the real and virtual interface was obtained in the reward subscale. In the interviews, almost all participants reported amazement when observing real levitation, but this wow effect did not seem to transfer to the VR condition. And also, the possibility of reaching into the display and directly interacting with the levitating particle was rated as an overall more rewarding experience. This graph shows the time participants spent playing each game in each condition. In the LeviShooter game, a ceiling effect occurred, where most of the participants spent the maximum allowed time of 5 minutes playing the game in both conditions. The results for the BeadBounce game, however, indicate that participants spent significantly more time in the simulator compared to the real interface. So in this paper, we investigate whether virtual prototyping can facilitate and encourage content creation for levitation interfaces. The results of the two user studies show that the Levitation Simulator can provide good predictions regarding the interaction with the real prototype. However, when developing and evaluating applications for levitation interfaces in the simulator, it is important to keep in mind the following differences. The lacking depth cues in VR might lead to an underestimation of the pointing performance of the users, especially for tasks with high index of difficulty. Also, real levitation triggers a wow effect that does not seem to appear in the virtual setting. And the immersivity of the VR environment might lead to an overestimation of the user interaction time with certain applications. On the example of levitating interfaces, we have demonstrated how virtual prototyping can be helpful in the development and design of user interfaces. And with this, we hope to inspire future research in modeling, simulation, and virtual prototyping of UIs. Thank you so much for your attention, and for more details, please check out the paper.